This is lecture 22, and this is going to be our final lecture, and that's going to be a shorter lecture. I want to just kind of finish up talking about some of the most powerful testing topics that we've been talking about, and this will kind of round out our hypothesis testing, draw it to a nice conclusion, and provide for a nice ending for the material. So last time we had talked about the Newman-Pearson lemma. And so we were considering a simple hypothesis. So let's just rewrite out what the Newman-Pearson lemma was. Lemma. And the Newman-Pearson lemma was concerned with finding the most powerful test for simple hypothesis. So what we said is consider a simple hypothesis test and the simple hypothesis test is where the null and the alternative both have one outcome. So our null here is h naught, theta is theta naught, versus some alternative ha, theta is, let's call it theta a. And we're going to use the likelihood ratio test so that we reject the null hypothesis if, in this case, lambda, our likelihood ratio test statistic, which is just going to be L of theta naught over L of theta A, right? Normally it'd be the MLEs, but if we just have one outcome or one option for each of our null alternative, we only have one value, so it's just theta naught is the MLE for the null hypothesis, and under the alternative, it's either theta, or under the kind of full space, it's either theta naught or theta A, and we're only really interested in the case where it's theta A, because if it's theta naught for the bottom, this whole thing is just 1. So this is kind of a review of last time. And we'll reject if this thing is less than or equal to some value c. And our kind of commentary is that we choose c so that our test is size alpha. And what that means in this case is that since we only have one possibility under the null hypothesis, that's the probability when theta is theta naught that we reject, which is that lambda is less than or equal to c, is going to be alpha. So the Newman-Pearson lemma, the punchline, which I haven't written, I've only written the kind of setup at this point, is that if we consider this simple hypothesis, theta naught versus theta A, and we're going to test it with this LRT, we're going to choose the cutoff threshold for LRT to ensure that it's a size alpha test, then the statement of the Newman-Pearson is that this is the UMP level alpha test. And so for a simple hypothesis test, we've determined that the uniformly most powerful test is actually just going to be the likelihood ratio test. That's nice, and it justifies why we're interested in this likelihood ratio, and it kind of ties everything nicely together, because the likelihood ratio brings together a likelihood function, brings together MLEs, and ties together a bunch of topics throughout the course. We also had a theorem last time, and I'll be real quick in writing this. The theorem is that LRTs are functions of sufficient statistics. And so that lambda, usually we write it as lambda of my sample, lambda of x, could be written as some other lambda star of t. And here, t is going to be my sufficient statistic for theta. And the proof of this, which I didn't really prove last time, but the idea is basically that the LRT the likelihood ratio test, and the statistic lambda in particular. Lambda is a function of the MLEs, and it's a function of the likelihood function, which is the PDFs. And all of those can be written basically as a function of a sufficient statistic. It's kind of the definition of a sufficient statistic in some ways. And so we can always, or we can typically rewrite LRTs as, instead of lambda less than or equal to some value c, you can write it as some condition on a sufficient statistic t. And that we're going to look at that a little bit more today. The topic of this lecture, the title of this lecture is Karlin-Rubin Theorem, or Karlin-Rubin, and that is going to be a theorem we talk about. It's going to talk about sufficient statistics, and it's going to generalize basically the Newman Pearson lemma to beyond the kind of simple hypothesis setting. So to set ourselves up for that, let's just review kind of the bigger picture here. Is our goal here is to find the UMP level alpha test. And if we have a simple hypothesis, we said that we have just stated the theorem, Newman Pearson theorem. And this theorem is going to tell us, basically says that the LRT is the UMP level alpha test for a simple hypothesis. And then Pearson says use LRT. And so we could talk about composite hypotheses, more complicated hypotheses that have more than one value in the null and alternative. And we could break it down into one-sided hypothesis. So like theta is bigger than some value or theta is less than some value. And we could also break it up. We could also look at two-sided hypotheses. And for one-sided hypotheses, the kind of topic that we're going to talk about in this lecture, we have a theorem called the Karlin-Rubin theorem. And the Karlin-Rubin theorem says use the LRT, or in particular it says a sufficient statistic. And so we could write this for the Newman Pearson lemma. The Newman Pearson says for simple hypotheses, the UMP level alpha, the uniformly most powerful level alpha test, is the LRT, which is basically a sufficient statistic, or based on a sufficient statistic. For one-sided hypotheses, we're going to have what's called the Karlin-Rubin theorem. And the Karlin-Rubin theorem says use the LRT, or again, base the test on a sufficient statistic. These are kind of equivalent things because the test statistic for the LRT is a function of a sufficient statistic. And so that's the topic for today. Two-sided hypothesis tests, unfortunately, it's not that simple. In general, there's not a UMP level alpha test. You have to restrict the class of tests more. You have to look at what's called unbiased tests, is typically the way one looks at it. So we'll just put a frowny face here. Beyond the scope of this course, not because it's that hard, but it's just we don't have time. In fact, we could talk about it. It's a little bit more difficult. What typically people do is they talk about what's called an unbiased test. So there are some more restrictive conditions on the test in order to restrict the set of tests so that we can actually find the best test among them. But for one-sided tests, we can actually get a uniformly most powerful test, a uniformly most powerful level alpha test that uses the Karlin-Rubin theorem. But in particular, we need a slight restriction on what we can say here, and the restriction is that we need what's called the MLR property. So we talked about this last time a little bit without context, but basically the idea is that this Karlin-Rubin theorem requires that the sufficient statistic has a certain property in order for the theorem to work. And basically the property is called the monotone likelihood ratio property. And well, let's write what it is. We talked about it a little bit last time. Let's just do a little bit of a review of what the MLR property is. Okay, so let's give ourselves a definition here. Okay, definition. Monotone likelihood ratio property. And so you can see from the name of it, it has to do with the likelihood ratio. This is typically denoted as MLR. And what do we want to say? Well, let's just write the theorem out. If f theta is a family of distributions indexed by theta, right? So we have some collection of distributions indexed by theta. This is very common, right? And so we could write, if I have two values of theta, theta 2, and theta 2 is going to be bigger than theta 1. If I have this family of distributions, I have some theta 2 and a smaller value theta 1. We say this family of distributions has the MLR property, or T, if I look at the ratio of likelihoods, that's the name, likelihood ratio property, L of theta 2 over L of theta 1, right? And our likelihood functions are just, this is kind of a really fancy way of saying we're just looking at f theta 2 of x over f theta 1 of x. All right, so we're looking at one particular, not looking at a joint distribution. We're just looking at it's a family distribution, so it's a 1x at a time, right? And we're going to look at basically the ratio of the PDFs at theta 2 and theta 1. Right, and you can think of that as L of theta 2 over L of theta 1 in some sense. So typically when we talk about the likelihood function, we're talking about some random sample. Here we're talking about only 1x, right? So this is some function of x. You can think about it as a function of theta, but this is a function, if I fix my theta 2 and I fix my theta 1, this is a function of x. And we say this has the MLR property if this ratio is a monotone increasing, is monotone increasing as a function of x. So that's the property. It's a little bit esoteric, but the idea is that this, we're looking at the likelihood ratio test. And so when you're interested in ratios of likelihoods, and we want the thing to be well behaved. We want it to be monotone, so the behavior is kind of well defined. It's invertible, and it behaves real nicely, right? Monotone functions, real functions are quite nicely behaved. And so if, what we're going to show in the Karlin-Rubin theorem is that if the sufficient statistic has this MLR property, the distribution of that sufficient statistic has the MLR property, we're going to be able to get a UMP level alpha test. So let's look at an example. Or let's just write out the theorem, right? Sure. Let's write out the theorem. So the theorem is called the Karlin-Rubin theorem. come on, Rubin, and named after Karlin-Rubin, two statisticians, and we're going to say consider testing a one-sided test, which is H naught. Theta is less than or equal to some value A versus the alternative, which is that theta is bigger than some value A. So we're going to consider this one-sided test, and the direction doesn't really matter. We'll talk about that in a second, but for now, just to consider the case where the null is less than A and the alternative is bigger than A. And let T be a sufficient statistic for theta, and the distribution of T has the MLR property. So this is why when we talked about the MLR property, we talked about it's just one X, right? It's not a whole sample, because what we're interested in is the MLR property only exists for univariate distributions, right? If you have multiple X's, you can't really define monotone for in a two-dimensional space. What does it mean for a function to be kind of monotone? It's a more complicated proposition. So the MLR property is really a property for univariate distributions or families of distributions. And the Karlin-Rubin theorem is going to say that our sufficient statistic has the MLR property. So T, our sufficient statistic, is typically a one univariate. I guess implied here is this univariate random variable. It has a distribution, and that distribution may or may not have the MLR property. So the kind of ratio of this thing may or may not be nicely behaved. If it does, then consider the test that rejects when, well, what would the intuitive thing to be? If T is sufficient, it tells us about theta, and we're going to reject when T is big enough. The idea being is that the null is that theta is small, and if T is sufficient and it has this increasing property, this MLR property, then large values of T are going to give us evidence of the alternative, and small values of T are going to give us evidence of the null. Now, if it turns out your sufficient statistic is decreasing, not increasing, so it's monotone, decreasing as a function of X, it has like the anti-MLR property. You can always just take negative T and then you flip things around. So it's not a huge deal. Because you can find this sufficient statistic that's monotone, either increasing or decreasing, you can always make it increasing. So we state it in terms of increasing because that's easiest. But the idea being is that we have the sufficient statistic, it's monotone, it has a monotone likelihood ratio property. We can make sure it's increasing by taking either T or negative T. And so we're going to assume it's increasing, which is why the MLR property is stated that way. And we're going to build the test so that if the MLR has, that if the sufficient statistic is large, we're going to reject the null because it's giving evidence of the alternative, and if it's small, it's giving evidence of the null. And we choose C so that the probability when theta is A, so let me just write probability when theta is A of that we reject is alpha, or we could say less than or equal to alpha, doesn't really matter. Then this is the UMP level alpha test. So Karlin-Rubin says that if I want to find the UMP level alpha test for a one-sided test, what I do is I find a sufficient statistic, that it has the MLR property. If I can find such a thing, then I'll just set up my test to reject correspondingly. If my alternative is that theta is bigger than some value, I'll reject when t is large. And I'm going to choose my cutoff for where I reject, right? How large t has to be to reject to ensure that I have a level alpha test. If I do this, this is the UMP level alpha test. So how does this relate to Newman and Pearson? How does this relate to other things? First of all, some notes here is that we could alternatively say test, say H naught, which is that theta is bigger than some value A, versus HA, which is theta is less than value A, right? So I could flip my null and alternative, right? So up here I stated in terms of less than, the null is less than A and the alternative is bigger than A. You can flip it so the null is bigger than A, the alternative is less than A. And so you can test that and say, let's say by rejecting when t is less than some value c, that's okay also. So my first note is that the Karlin-Rubin theorem doesn't, I mean, you can flip my null and alternative, it doesn't really matter. I would just flip my test. Instead of testing if t is bigger than some value c, you test if it's less than some cutoff value c, and you choose that value c, again, to ensure the size of the test that you want. My second note here is that this is basically the LRT. So just as in the Newman and Pearson case, when we did the simple hypothesis, the LRT was the UMP level alpha test. For the one-sided composite hypothesis, it's also going to be the LRT is also the UMP level alpha test. The idea being that, why can I say this is based on the LRT? Because the LRT is based on a sufficient statistic on the, let's say, it doesn't really matter, on a sufficient statistic, right? This is why I emphasize that theorem again, which we said way back up here, is that the LRT is a function of a sufficient statistic. So if I'm going to build my test, as I do in the Karlin-Rubin theorem, to reject based on a sufficient statistic, that's basically doing the LRT. It's just another way of doing the LRT, right? So these things are pretty much the same thing. I could write this in terms of the LRT, but it's actually much easier typically to think about it in terms of sufficient statistic. And so that's why it's stated that way. But because the monotone likelihood ratio property is going to basically ensure that there's going to be a one-to-one correspondence between rejecting based on sufficient statistic and rejecting based on the LRT, because they're going to be one-to-one functions of each other. The LRT is a function of the sufficient statistic, and the sufficient statistic therefore can be written, as a function of the LRT. So we can look at some examples here. We'll kind of close out the lecture, the short lecture today, just kind of close out everything together by looking at some examples. So here's an example. Let's assume data comes from normal mu sigma squared. This is a classic test. We've done this a million times, right? And we're going to say where sigma squared is known. So the only unknown parameter here is mu. And so let's say 1 here. Let's test H naught, which is that, mu is smaller than some value A, versus the alternative, which is that mu is bigger than some value A. There's a classic test you would do in, say, introstats. Is my mean bigger than this? Is my mean smaller than this? What does the Karlin-Rubin theorem say about the best test to use here? Well, 1, we can not write 1 again. Let's say we know that x bar is sufficient for mu. And the question is, does x bar have the MLR property? So we need it to be sufficient. Sufficient, does t or x bar in this case have the MLR property? And I'm going to make a claim here, and we'll go and write the little theorem out and prove this in a second. We know x bar is sufficient. I'm going to say x bar has the MLR property because it follows an exponential family. And so not surprisingly, the exponential families typically are going to have the MLR property. We'll talk about exactly, we'll defer this for a second. But because x bar is sufficient, I'm going to claim in a second that x bar has the MLR property. So recall that the MLR property is a function of the sufficient statistics, not about the underlying x sub n's. It's about the sufficient statistic. X bar in this case is normally distributed. That's certainly an exponential family, and we'll claim that this has the MLR property because basically it's an exponential family, so it's going to be really, really easy to check. And so the UMP level alpha test is to reject when x bar is too big, right? My alternative here is that mu is large, and so that I'm going to reject when x bar is bigger than some value c. And how do I choose c? C is chosen so that the probability when theta, or I'm sorry, in this case we call it mu, when mu is a of rejecting, that is when x bar is bigger than c, is alpha. Well, x bar has a normal mu sigma squared over n distribution, right? And so here's what that thing looks like. This is mu, has variance sigma squared over n. And so this is the distribution of x bar. All right. And so I want to choose my c so that when mu is a, I want the probability that x bar bigger than c is alpha. So basically I want to choose my c here so that this probability alpha, right? So it starts to feel a lot like an interest-stats problem where we say, you know, I want to choose my cutoff value here. I want to find the value so that when x is a, the probability of x bar being beyond, I'm sorry, when mu is a, the probability of x bar being beyond c is alpha. So if I look at c is going to be, one way to look at this is if is that x bar bigger than c is equivalent to, what do we want to say? It's equivalent to x bar minus a over sigma over root n being bigger than, let's call it some c star, some other c. This thing is a normal 0, 1. And so this thing is what we call z alpha. And so my test, which is x bar bigger than c, is the same thing as saying this thing. So c is going to be, we just solve back for it, it's a plus z alpha times sigma over root n. So that's what my value of c is. Alternatively, you can think about it in terms of the second way here, which is that the test would be you calculate x bar minus a over sigma over root n, and you see if it's bigger than c alpha. You see it's bigger than the alpha quantile here. You see if it's bigger than whatever you call this cutoff value where we have alpha probability above it, right? So that's exactly what we do in the interest-stats course, right? Interest-stats course, you say, well, the test if mu is less than a, mu is bigger than a. So a is my test value. I'm going to calculate x bar minus a over sigma over root n. You call that what do we call that? A t-statistic. Well, we didn't. I mean, it's like a t-statistic. If you didn't know sigma, it would be t, but it's a z-statistic, so it's called. And you see if that's bigger than this cutoff value is like 1, if it 1 to 95, when alpha would be 0.05, this would be like, what is it, 1.6 or something like that, right? So the stack you would do in interstats, and the Karlin-Rubin says that that is the UMP level alpha test. So this all required that, of course, in our second step here, that X bar has this MLR property. And they made some claim that, well, for exponential families, this is going to be pretty easy to test. And indeed, it is pretty easy to test. So the theorem is, let's say, exponential families and MLR. It's a little more complicated than saying, oh, exponential families have the MLR. Not all of them do, but typically it's pretty easy to check. So if we have this family, all right, so we have our family distributions, F indexed by theta, and an exponential family. So it's not only a family distribution, but it's an exponential family of distributions. So that F theta of X is, what does an exponential family look like? C of theta, H of X, exponential, W of theta. And normally I'd write T here. I'm just going to write X. So it's going to be of this form. So for example, well, we'll look at X bar. We'll follow this distribution, right? So normally it could be some T of X, but we're just going to say it actually has to be just X in this case. If this is the case, so the family distributions is an exponential family where T of X is just X, then if W is increasing in theta, this family has the MLR property. We can look at the proof of that. Not too hard to show. So the MLR property says, well, let's just write it as, I have some theta 2 bigger than theta 1, and I look at F theta 2 of X over F theta 1 of X, and this is, well, according to if it follows my exponential family form, it's C of theta 2 over C of theta 1, H of X over H of X, well, that will go away. Exponential of, well, let's write this out, just an easier form, exponential of W of theta 2 times X over exponential of W of theta 1 times X, right? And so I get C of theta 2 over C of theta 1. My H of X's cancel, and I can write this as exponential of W of theta 2 minus W of theta 1 times X. So I can combine those. And my claim and my theorem is that W is an increasing function in theta. So what does that mean? If W is increasing, then the definition of an increasing function is that if I have some theta 2 that's bigger than theta 1, increasing means that W preserves that. W of theta 2 is bigger than W of theta 1. And so this thing here is bigger than 0. W of theta 2 minus W of theta 1 is bigger than 0. And so this whole thing looks like, as far as a function of X, which is what the MLR property is talking about, it looks like e to the AX, where A is bigger than 0. And so that's an increasing function, right? This is what it looks like. It's like e to the AX. It's some increasing function. So, as a function of X, and so this ratio, this likelihood ratio, is an increasing function of X, therefore it has the MLR property. So what we need to show that, if we have an exponential family of this form, and W is increasing, So you need both those things. You can write it as an exponential family in this form, where instead of t of x, just x, and it's an increasing function in theta. W is an increasing function in theta. And then we have the MLR. So in this example, I did a little sleight of hand here because in this step here, you do actually have to show that x bar has this MLR property to do this thing. But of course, what we said, so let's just revisit that example. Revisit x bar. What we had said is that, right, we know that x bar in this case has a normal mu sigma squared distribution. And so if you look at the PDF, so the ML, we want to know, does the distribution of x bar have the MLR property? And mu is our unknown here. So in this case, if we look at ft, so this is going to be our PDF, not of the individual x of n's, but the PDF of x bar, and it's indexed by a parameter theta. This thing is going to be what? So what's our PDF? This x bar should be 1 over sigma squared. Should be mu sigma squared over n, right? So it's root 2 pi sigma squared over n, something like this, exp to the -1, or let's write it like this, like that, t minus mu squared, right? So that's our PDF of x bar, right? Where t is the variable it's standing in, right? I guess I called it x before. It doesn't really matter. You can call it x if you want. If that makes you happier. We can call this x. I don't want to confuse it with the x of n. So this is really x bar. So maybe we'll just write f of x bar. Sure, that works actually. So that's the form of it. We know this is an exponential family. The question is, so let's just write that. Check exponential family because it's a normal distribution. The question is, does it have the MLR property? And we needed to check, in our theorem, we need to check that W of theta is increasing function of theta. Well, theta in this case is mu. So let's expand this out. The constant up front, which doesn't depend on mu or x, we just don't really care about, proportional to exponential of negative n. Oh, let's tediously do this out. X bar squared minus 2 mu x bar plus mu squared. And anything that doesn't depend on mu or x bar, I guess everything here does, right? So can we get rid of anything? Well, we don't really care about the mu. I guess we only care about we want to write this thing as, so this thing is, let's be a little more careful here. Let's just not make this too confusing here. This is 2 pi sigma squared over n. Let's just keep that constant out front, right? All right, we're trying to write this in the canonical form for the exponential family, right? So we need to identify c, h, and w, right? So this thing out front is basically going to be c of, well, no, this is going to end up, actually doesn't really matter where it ends up. Could have been c, could have been an h, doesn't depend on mu or x. So let's just write this out. So there's this 2 pi sigma squared over n. I think one more step will do it for us. There's this exponential negative n over sigma squared by x bar squared. Let's pull that out. Separate, that's going to be basically h. And we'll get the last term here. So that's going to be, this thing goes to there. This mu term, we can pull out as exponential of negative n over sigma squared times mu squared. That's going to end up in c of mu. And then this final term here, will end up over here as exponential of, what is this, negative n over sigma squared times negative 2 mu, so negative cancels, 2 mu x bar. Okay, So let's identify our parts. We call this thing h of x bar, this thing c of mu. This thing here is called w of mu, and this thing is basically x, right? And so what do we get? W of mu is 2n over sigma squared times mu is increasing in mu. Bob's your uncle. It all works out, right? So this w is increasing, therefore x bar, because it comes from an exponential family, has the MLR property. Therefore, we can invoke the Karlin-Rubin theorem and say that, where is our example? If we want to test this one-sided hypothesis, we can do that. So that's kind of a nice little example, and brings it really back kind of to interest stats, where you would get, you know, this is the test that you would develop for in an interest stats course for the one-sided z-test, and it is, according to Karlin-Rubin, it is the UMP level alpha test. And so that nicely kind of concludes things here. You know, so for simple hypotheses and for composite hypotheses, or for one-sided composite hypotheses, as long as you have a little bit of a condition there that they're nice enough from an exponential family, it's pretty easy to find the most powerful test. And these tests, when you develop them, are going to be tests that you recognize. And so this really nicely kind of circles back to the test that we all kind of recognize. Here's the z-test. If you didn't know sigma squared, you would end up deriving the t-test. So that's a nice little conclusion for our theory of hypothesis testing. I'm not gonna continue on here today. I'm gonna end it at this point because this is just a nice little conclusion to the unit on hypothesis testing, and this is a nice place to end the course here.